fun thing you can do because of superposition is you can make stationary waves, sometimes called standing waves. And here's the version on a string. So if you've seen this in the lab, you'll know that you clamp one end, the other end goes over a pulley with masses on, and this allows you to keep a constant tension in the string and also to know what the tension is. The tension will be equal to the weight of the masses, and that's very important if you're doing AQA. Then you have a vibration generator here that pushes the string up and down, and it's attached to a signal generator, and that allows you to control the frequency. So you can change the frequency that the string is being pushed up and down, which changes the frequency of the wave travelling along the string. There are certain frequencies that give you a nice pattern on the string, so that's where you get a shape that appears not to be moving. The lowest frequency that's going to give you a nice pattern will give you this pattern, and it's called the fundamental frequency. The next frequency up that gives you a nice pattern will give you this pattern. The next one up from that will give you this pattern, and so on. So you can see that we've started with half a wave, then 2 halves, then 3 halves. And so in general, you will get a stationary wave if the length of the string is equal to a whole number of half wavelengths. And this pattern results from the fact that both ends of the string are fixed. In this pattern, the wavelength is half that of this one, so the frequency will be double it. In this one, the wavelength is a third that of this one, so the frequency will be 3 times it, and so on. Now these fixed points at the end never move, but neither do these points in the middle. They never ever move, and so they're called nodes. I don't know if it's short for no displacement, but that certainly helps to remember it. And then these points that travel furthest from the centre line, these are called antinodes. And then all the places in between they're not going to have no displacement, they're going to have some displacement. So let me take, for example, that point there. That never gets higher than that, and then it's going to travel down to there, and then it's going to travel back up again. So it's not stationary, but it doesn't get the full range of motion that an antinode does. Okay, the practice question's a calculation, but first, the most common question for stationary waves on a string is how do they form? And this is always 3 marks, so it goes like this. A wave is sent down the string. It reflects at the other end and superposes with the original wave, creating a wave with nodes and antinodes. So once again, your 3 marks are: a wave is sent down the string, first mark. It's reflected and superposes with the original wave, second mark, to create a resultant wave with nodes and antinodes, third mark. Okay, time to have a go at the practice question. So we're told the frequency and we want the speed. So it looks like we're going for this formula, but we don't know the wavelength yet. Now we look at our diagram. But one wave is from here to there. So that means that lambda is 60 centimetres. And so that's the speed of the wave.